Hi all, welcome to our second revision lecture on topic 2, which is atomic structure. So let's get cracking with 2.1, which is the nuclear atom. Here's our study guide. It's all pretty basic. So we've got basic atomic structure with protons and neutrons in the middle and electrons around the outside. We've then got that as connected to how we depict nuclear symbol notation. Then we've got mass spectra as it connects to calculations. Okay, let's continue with basic atomic structure. So hopefully you should all be aware that there are three main types of, and of course I'm going to do different colours because I'm mainly retentive like that. Protons, which have a positive charge, neutrons, which have zero charge, and electrons that have a negative charge. The simplest atom that in its most common isotope has all three of these is helium. So helium has two protons, two neutrons. Oh, sorry, no, that's not my neutron colour. Green is my neutron colour because green is a neutral colour, or that's what my brain has decided this morning. Then around the outside, I have two electrons. So this block of matter in the middle, this is our nucleus. Oh, sorry, haven't switched off to my pen. So this block in the middle is our nucleus. So the nucleus contains like north of 99% of the mass of the atom. Only a tiny amount of the mass of an atom is tied up in its electrons. Most of the time in chemistry, we are looking at the reactions that electrons do, so where my electrons are transferred to and from, and the bonds that those electrons form. However, in the energy option, we did look at some nuclear reactions. Okay, let's continue on. Okay, so how we represent elements. This is one of the main ways we represent elements. This number up the top here is our mass number, which is protons plus neutrons. This guy down here is our atomic number, which is just equal to our number of protons. This X here is our symbol. So for example, there are three main different isotopes of carbon. They are carbon 12, carbon 13, and carbon 14. Now, carbon by definition as an element has 6 protons. If it doesn't have 6 protons, it's not carbon. So those are the symbols for each of those carbon isotopes. Let's continue on. So mass spectrometry, you don't need to know the details about how this works, but I personally find it easier, particularly when you start talking about mass spec in like spectroscopy for organic compounds. So you start by, and again, you know how I love drawing, you start by injecting your sample into the ionizer, and basically that fires electrons at the sample until they become positively charged. They then, oh, be good if I could draw like a semicircle. So then those positively charged ions enter a curved tube, and around the outside of that tube there is a variable magnetic field. So let me just annotate that. So the stronger that magnetic field is, the more it bends the particle, the charged particle that's been put in. So sorry, I'm just trying to think of a way to explain this. So depending on the amount of magnetic field, if my field is too weak, the ion doesn't get bent enough and it crashes into the side of the tube. If it gets bent too much, so as I said, if it gets bent too much, it crashes into that near wall. But if you Goldilocks it, if you get it just right, it goes straight down the middle of this curved tube and ends up getting detected. So mass spectrometry separates fragments on the basis of mass, and they have to be these positively charged fragments in order to be accelerated by the magnetic field. So they have to be positively charged, and mass spec then separates those, and we get a visualization based on, basically for atomic theory, the fraction of the ions, these atoms that are introduced and then ionized, on the basis of mass. So what does that look like? We could end up with something like this. So what we've got here is a range of different zirconium isotopes, and then we've got their percentage frequencies. So how I then calculate relative atomic mass, we do a weighted average. So it would be 90 times 51.5 plus 91 times 11.2 plus, and I'm going to run out of room, I can see already, 92 times 17.1 plus 94 times 17.4 plus 96 times 2.8, then divide all of that by 100. The reason I divide by 100 is that these percentages, I had to multiply them by 100 to get them into a percentage form, so I need to divide by 100 at the end. Now, I don't have a calculator on me, but for our purposes, the actual answer to this question doesn't matter. It's more that you know how to do this working. If you are asked to do one of these on the exam, they will not give you a set of numbers that gives you the answer that's on the periodic table. So the answer that's on the periodic table for zirconium is, and I've got that one here, if I can find zirconium, it's 91.22. Now, the answer that this calculation would come out at would be close to 91.22, but it wouldn't be exactly. And in the mark scheme for this question, if it were to come up on the exam, it would say, do not accept 91.22. This isn't a can I look up on the periodic table question. This is a, let me just switch to my laser. This is a do you know how to complete this calculation question. Alrighty, let's move on. Okay, so we discussed the structure of the atom, including where the electrons are located. We talked about AZ notation. We talked about the mass spec, and we talked about how we calculate. Yes, so that is just our guidance. So those values are in section 4. I talked about how we kind of ignore the mass of the electron. Then we don't need to know about specific examples of isotopes. And I went into more detail about how a mass spec works than you need, but you don't need to know the details of how that works. Okay, let's continue on to topic 2.2, which is electron configuration. So we're going to talk about emission spectra, particularly for hydrogens, and we're going to link that to the electromagnetic spectrum. We don't require the names of the different series of the hydrogen spectrum. We're going to talk about shells, subshells, and orbitals. We're going to link relationship between colour, wavelength, frequency, and energy. We're going to talk about continuous versus line spectra and hydrogen atom. We're going to talk about the shapes of P, X, Y, and Z, and also S. And we're going to talk about principles, rules, and exclusion principles. We're going to talk about electron configs, orbital diagrams, and copper and chromium. A more in detail version of this is the electron config video that is on my channel. This is going to be a shorter version of that. Okay. So the electromagnetic spectrum. And so we basically have, from down here, we've got radio, then micro, then IR, Vis, UV, X, and then gamma. So the visible spectrum, if I expand that out, I end up with my rainbow. So basically, if you are Isaac Newton, you basically took a prism and you split that visible light into the spectrum, like the cover of Dark Side of the Moon. And then basically what we need to know is that as I go from radio, micro, IR, as I move from left to right along this line, my energy increases. As I move from left to right, my frequency increases. And as I actually move from right to left, my wavelength increases. So one thing that I'm actually going to ask my Year 9s to do, I'm actually going to ask them to use their microwaves to find the wavelength of the microwaves that their device is creating, and then use that to calculate the speed of light, which is kind of cool. There will be details on how to do that in a video that I'm about to produce for my Year 9s. But generally, this is what the electromagnetic spectrum is. This is what it looks like. There is a diagram very similar to this without my green annotations on it in the data book. This is not something that you need to have memorized, but you actually do need to know these green lines. So what's happening to my energy, frequency, and wavelength as I move along this spectrum. All right. So emission spectra. If we go back to that Bohr picture of the atom, so I've got my N equals 1, which is the ground state for that electron. Then I've got 2, 3, and 4. Let's just do those ones for now. So an emission spectra, let's say I've got an electron that is sitting up at this N equals 3 energy level. After a certain amount of time, it will fall back down to the ground state. And as it does that, it will release a wavelength of light. The same thing goes if I've got an electron at the N equals 4 and it falls back to the N equals 1, it will release a certain wavelength of light. And if I've got 1 at the n equals 2, it does that also. So what that would basically look like is an emission spectrum where I've got some orange light being released, I've got some green light being released, and then I have some purple light being released. Now, the energies of those wavelengths of light correspond to the different energy levels that that electron can fall back from within the atom. All right. Emission spectra versus absorption spectra is really interesting. So we start with, and I'm just going to laser point on this one, we have our continuous spectrum. This is our Roy G. Biv. So red, orange, yellow, green, blue, indigo, violet. The emission lines are what are caused by those electrons falling back down. Because that falling down releases the energy. So emission lines are a release of energy. Absorption lines are in some ways the more important ones. So absorption lines are what happens when an element absorbs that energy. So this is my electrons jumping up. Up, which is an so absorption spectra are super important because they're used a lot by NASA to actually determine the chemical compositions of stars. So if we know the set of lines that hydrogen absorbs, and if we know the set of lines that helium absorbs, we can actually measure the intensity of those lines and work out the chemical composition of that particular star, which is kind of cool. And also, the next step on from that, you don't need to know this, when you look at the redshift, so the Doppler effect on that set of lines, you can tell how far away that particular star is. So it's all really cool. And it all ties back to that Bohr picture of the atom. Okay, so when it comes to shells, subshells, and orbitals, at least for shells and subshells, I find it easiest to think about it in terms of a periodic table. Oh, yep, that one was incredibly well drawn. Congratulations, Amy. So a shell of the periodic table is just one of these lines of elements. So that, for example, is the second shell. The subshells, let me switch back to my highlighter and let me change the colour. The subshells are the blocks. So that one there that I've just highlighted is the P subshell. Then once we start talking about orbitals, we need to zoom in. So let's just look at this 2p subshell. So the 2p subshell has 6 electrons in it, and that is 3 orbitals. So each orbital can hold 2 electrons. Sorry, excuse me. So, yeah, that's basically it. So shells are the largest division, subshells are smaller, and then orbitals are smaller than that. Let's continue on and talk about how we fill electrons into these guys. So the orbital shapes, you need to know how to draw an s orbital and a px, py, and pz. So all of these are centered around a set of axes. And unlike most axes that you think about and draw, it's going to be a 3D orbital. So the s orbital, remember those orbitals are probability regions where we find our electrons. So our s orbital is just a sphere. It's that 3D circle shape around the center of that XYZ set of axes. Px, Py, and Pz. And yes, you know how I am with drawing. We saw that earlier with the mass spec. So I've got Y, Z, and X. The Px orbital, which I'll do in green, is this infinity shape that has its node at the origin. I think I actually made these shapes with balloons back last year, where we blew up balloons. Py is that exact same shape that's centered around the y-axis. And then Pz, which I'll do in purple, is this exact same shape around the z-axis. The important point to note is what's called the node. And let me switch to my laser. It is this, the fact that this crossover, and I know I haven't quite drawn it right on the z orbital, this node exists at the, so our node is this thing here. Now, you just need to know that the px orbital is along the x-axis, the y is along the y-axis, and the z is along the z-axis. So the z-axis is that 3D, makes it a 3D shape rather than a 2D, either circle or infinity symbol. These are three-dimensional shapes. The d and f orbitals, their shapes just get weird. So you don't need to know how to draw the d or f orbitals, but you do need to know how to draw the s and p orbitals. Okay. So there are three different principles, rules, principles, whatever, that we use to work out how electrons are placed within the atom. Aufbau says that the lowest energy first. So 1s gets filled before like 2s. 2s before 2p. So let me just rub this out. So that is, you might have seen this before, 3p, 3d, 4s. So what we then do is we draw the diagonal arrows down. Hund, I call it single occupancy. So for example, if I'm looking at 2s and then 2p, remember we had that px, py, pz in the 2p. If I'm filling in electrons, I fill up the 2s first, according to Aufbau, and then Hund says that I do single occupancy on the 2p orbitals before going back and filling up the second slots in each of those orbitals. What Pauli talks about relates to the fact that in that last square, when I was looking at, for example, one of my 2p orbitals, I have one electron that's got up spin and one electron that's got down spin. They have to be spin opposed. Now that's because according, like quantum mechanical type reasons, I can't have two particles with exactly the same characteristics in the same location. So that spin is Pauli. So my electrons have to have opposite spin in order for them to occupy the same orbital. Okay, let's continue on. Okay, so something that will be super helpful for us when doing this is for you to have a periodic table on hand to look at. So I'm just going to quickly run through how to do electron configs. If you're after more of an in-depth explanation, my extended video on electron configurations that's already up on my channel is going to be helpful to you here. So let's look at aluminium. So aluminium has 13 electrons we're trying to place. So if you remember Aufbau from what we were looking at earlier, 2s, 2p, 3s, 3p, 3d. Now we only need to get up to there, but let me just put in 4s for completeness. So I fill 1s first, then 2s, then 2p, 3s, 3p, 4s. So let's start. So I have 13 electrons I need to place. If I put 1s2, that means I've got 11 left over. I go 2s2, that means I've got 9 left over. 2p6, that means I've got 3 left over. Then it goes 3s2 and I've got 1 left over. Then 3p1. That is the full electron configuration. It is showing me all of the electrons and where they're located. But as I've said on multiple occasions before, scientists are deeply lazy people. We will find shortcuts if we can to get around writing full electron configs. That's where condensed configs come in. Condensed are also sometimes called noble gas. Noble, not Nobel, gas. So let's look at, again, aluminium. So what you basically do is you go, okay, so our outer shell, which is where all of the chemistry happens, we need to see that. But in terms of what's going on inside of that outer shell, it's basically a neon atom. So it's a neon electron config with a 3s2 and a 3p1 outside of that. So yeah, that's basically how you do your noble gas configs. You need to be able to recognise and write these. Okay, so because of course there are some exceptions. So we are going to talk about chromium and copper. So what we've got here, I am going to write the 4s and the 3d for each of these guys, and I'm going to draw my little squares. So I have 4s, and then 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so chromium, if you just look at the outer shell of chromium, it's got 1, 2, 3, 4, 5, 6. So 6 electrons split over the 4s and the 3d subshells. So if I were just going by that lowest energy first, I would say that the structure for chromium, chromium's on this side. So 1, 2, 3, 4. But if you remember, Hund said that single occupancy was preferred. What happens is that this second electron in the 4s doesn't the energy of this is actually lower if that electron is actually a single occupancy in the 3D. Imagine it, and this is going to be a very Melbourne-specific reference. This is the difference between being in a share house in Richmond compared to your own flat in Hawthorn. It's the next suburb out, so it's slightly further away, but you're on your own, so it's easier. So that's what happens with chromium. This second 4s moves out to live in the 3D so that they're all living alone. That is energetically favourable for the chromium atom. Copper does something similar. So copper has 2, 4, 6, 8, 10, 11 electrons split over these guys. So let's again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And hopefully you can see where this is going. So what happens? My second 4s electron moves out and pairs up in that 3D. That's because that 3D subshell, once it's filled, again, it's got that, it's energetically favourable once I've filled that 3D shell. Sorry, 3D subshell. Once I've filled that 3D subshell, that's energetically favourable over having a filled 4s and then an incomplete 3D. And the electron configs of these are, and I'm just going to do noble gas. So I've got argon 4s1 3d5, and this is argon 4s1 3d10. Okay, cool. Awesome. So we talked about emission spectra, we talked about hydrogen, we talked about electromagnetic spectrum, emission spectrum, frequency, wavelength, colour. We talked about continuous versus line spectrum. We then talked about energy levels, SPD, orbitals, shapes of orbitals. We then talked about Aufbau, Hund and Pauli and how it relates to electron configs, orbital diagrams and configs of copper and chromium. Thank you so much for listening to this one, guys. We'll have a Zoom chat to talk through any questions you've got about these. Let us know if there's any specific exam questions you'd like to take a look at, and I will see you next time. Have a great rest of your day. Bye.